Our second invited speaker is Dr. Dongmin Im from Samsung Advanced Institute of Technology. He will be talking about analyzing the internal resistance of sulfide-based solid-state batteries. Please.
Okay, hello everyone. My name is Dongmin Im, and I'm representing Samsung Advanced Institute of Technology. My talk today is about the internal resistance analysis of our solid-state battery. I'll give you an introduction of solid-state batteries and our own sulfide-based solid-state batteries. And then I'll talk about the resistance analysis. Okay, here's a comparison between conventional lithium-ion battery and solid-state battery. We have a cathode and an anode. That is the same, but liquid electrolyte and separator are replaced with solid electrolyte in the case of a solid-state battery. Since we do not have volatile organic electrolyte, the safety will be better. On the other hand, you might need to see that it is very difficult to completely fill the void spaces with solid electrolyte. There are always some grain boundary resistances and also the resistances between solid electrolyte and other components. Anyway, solid electrolyte is mechanically robust and is a kind of single ion conductor. So it is believed that it can handle the lithium metal anode very well. Lithium metal anode can offer much higher energy density than conventional graphite anode. You can see in this illustration that the volume of anode is substantially reduced when we use lithium metal anode. We can increase the cell energy density more if we employ the anode-free system where lithium metal is not present at the time of cell assembly. Instead, the metal is plated while charging the battery. This design can also save the production cost significantly. Here's the design of our own solid-state battery. We employ a sulfide-based electrolyte, and the cathode is a composite, and the anode is a silver carbon nanocomposite. This silver carbon layer is 5 to 10 micrometer thick, and it facilitates the smooth lithium metal deposition. This slide shows how this system works very well. In the first charging process, a dense lithium metal layer is deposited between the silver carbon layer and the source current collector. No lithium metal is found above the silver carbon layer. Some silver is dissolved into the lithium metal during this process. If we discharge the cell again, the lithium metal layer is completely removed. Some silver is accumulated at the bottom of the silver carbon layer. With this design, the probability of lithium metal penetration through the solid electrolyte is significantly reduced because the silver carbon layer is blocking the direct contact of lithium metal with the solid electrolyte. This process can be repeated many times. Even after 100 cycles, we can still see a very dense lithium deposit after the charge, and it is completely cleared after the discharge. We prepared a bicell with this design. We laminated a double-sided cathode, 2 solid electrolyte layer, 2 silver carbon composite layer, and 2 source foils. Then the assembly was pressed with a warm isostatic press. After the isostatic press, the cathode becomes very compact and the void spaces in the electrolyte layer almost disappeared. The sulfide-based electrolyte undergoes plastic deformation during this process, and consequently, the grain boundary resistances and other interfacial resistances are going to be minimized. we could cycle this bicell more than 1,000 times. Although it showed a signal suggesting some microshort circuits in the end, the coulombic efficiency was maintained over 99.9% until about 800 cycles. While we could get an excellent cycling performance, the rate capability was not as good as that of conventional lithium-ion batteries. If you look at the discharge profile obtained at 1C, the capacity loss is not so high, but the polarization is quite large. Also, this is the profile obtained at 60 degrees C. We typically see more energy loss if we run the cell at room temperature. So the purpose of this work is to find out what is the origin of this high polarization at large current. Many people suspect that the lower conductivity of solid electrolyte is responsible for the low rate performance, but that is not true in this case. Typical ionic conductivity of organic electrolyte is in the range of 10 millisiemens per centimeter, but the transference number for lithium ion is only about 0.2 or 0.3. So the effective conductivity would be a single digit in terms of millisiemens per centimeter. On the other hand, the conductivity of a sulfide-based solid electrolyte, such as azurite, is at least 2 millisiemens per centimeter or higher. And the transference number in this case is close to the unity. Then the effective conductivity would be more or less the same as that of liquid electrolyte. Moreover, if we consider the concentration polarization, the actual lithium-ion conduction should be faster in the case of solid electrolyte. Overall, we cannot say that low lithium-ion conductivity of solid electrolyte is responsible for the unsatisfactory rate performance of solid-state batteries. We also know that some commercial solid-state batteries, such as thin-film batteries, show good rate performance. They are prepared with vacuum processes, so all the components are dense and the interfaces are very good. This suggests that the internal resistance would be an important reason for the low rate performance of most bulk-type solid-state batteries. Then, which interface is responsible? There are many resistance components in our solid-state battery. If you look at the cathode, there are charge transfer resistance on the surface of a cathode active material, and bulk and grain boundary resistances for the solid electrolyte. If you look at the solid electrolyte layer, you can see that there are bulk and grain boundary resistances for the solid electrolyte. And we have to consider the charge transfer resistance at the anode. In this work, we focused on figuring out the influence of each resistance component as quantitatively as possible. Since the lithium ion is going to be reduced at the interface between solid electrolyte and the silver carbon layer, the movement of metallic lithium through the silver carbon layer should be considered too. But this behavior is quite complicated, so it is not included in the scope of this work. The first thing we can think about is the AC impedance analysis of a full cell. But the cathode is a good electronic conductor, and the silver carbon layer is also a good electronic conductor. So if we take the full cell AC impedance, then we can get only the information on both sides of the solid electrolyte layer. So it's not gonna revealed the information inside the cathode. As you can see in the right side, the actual Nyquist plot is very simple. It's very difficult to get the resistant information of each component separately from this plot. So we decided to measure the resistances one by one. All the data taken here from now on was taken at room temperature. The easiest part was the electrolyte layer. We just prepared a solid electrolyte pellet and pressed it with a warm isostatic press. Platinum was coated on both sides of the pellet. The total resistance measured in this way was about 56 ohms per centimeter. Since the thickness of the electrolyte layer in our solid-state battery is only about 50 micrometers, so we can estimate that the resistance for the electrolyte layer would be less than 4 ohms per centimeter in actual cell. The next one was the charge transfer resistance at the anode. We designed a special symmetric cell for this measurement. Silver carbon layers were coated on both sides of the electrolyte pellet, and it was pressed with a warm isostatic press. Then lithium metal foils were laminated on both sides of it and pressed with a cold isostatic press. During this process, the lithiation of silver carbon layer happened. If we look at the Nyquist plot, although the presence of small semicircle indicates that the process is more complicated than expected, we could reach the conclusion that the overall charge transfer resistance could be about 20 ohms per centimeter in this way. Okay, so we determined the resistance of electrolyte layer and the charge transfer resistance at the anode. So the next one was the charge transfer resistance. Actually, the next one was the cathode. Cathode is electronically conductive. It contains conductive agent, and the cathode active material itself is conductive. So we cannot get the information inside the cathode with this simple configuration. As an indirect method, we adopted a transmission line model to describe the composite cathode. There are two parallel transmission lines in this model. One represents the electronic conduction, and the other represents the ionic conduction. The electronic conduction is non-blocking, but the ionic conduction is blocking. A mathematical model is well established for this case. If the electronic conductivity of the cathode is too good, this model does not work. So for the measurement, the conductive agent should be removed, and at least the 50% of the volume should be occupied by the electrolyte. The actual curve fitting is very complicated, but it is achievable with an iteration process, for example. But there are many other methods for the curve fitting. And in our previous work, we demonstrate that this method could be used to study the influence of chemical degradation at the interface on the bulk and grain boundary resistance changes. So now we applied this transmission line model to determine the bulk and grain boundary resistance of our solid electrolyte inside the cathode. We prepared a composite pellet comprising 50 volume percent electrolyte and no carbon. The measured total resistance is about 170 ohms per centimeter. But after the adjustment, considering the actual cathode thickness and the electrolyte volume percent, it would be only about 28 ohms per centimeter. Since the whole current is not going to flow the entire cathode, the effective resistance for the calculation of polarization is going to be about 10 ohms per centimeter. Actually, this number should be higher if we consider the increase in the tortuosity with decreasing the amount of electrolyte. Finally, we are currently trying to measure the charge transfer resistance inside the cathode. This is the most difficult part since we need to vary the state of charge for the measurement. I mean, we need a cell that can be actually charged and discharged. This work is still ongoing, but preliminary result with this kind of cell indicates that the charge transfer resistance in the cathode is at least 100 ohms per centimeter. That means this resistance is higher than the sum of all other resistances. The reason should be further explored, but it can be from the insufficient physical contact at the interface, or it can be from the chemical degradation at the interface. If we look at this cross-sectional image, the physical contact looks good, but it is too early to say that this is a true reason. Okay, here's the summary of this work. You can see that the charge transfer resistance in the cathode is the dominant one. Also, the charge transfer resistance at the anode and the grain boundary resistance of the electrolyte inside the cathode are also important factors. We cannot move away them for the consideration in the case for the polarization decrease. Those three resistance components should be significantly improved to get a good rate performance in solid state batteries. The migration of metallic lithium in the silver carbon layer should also be explored, but currently it is difficult to say how much it will affect the rate performance of the cell. Okay, that was the summary of my talk, and all this is a repeat of what I mentioned in my previous slide. Thank you very much for your attention, and I'll be happy to answer your questions.
Thank you, Dr. Im. We have plenty of time, so please ask any question. Dr. Im, I have several questions. Very systematic and interesting analysis, I think, for the deconvoluting every resistance. I think the formation of an interface between silver carbon layer and lithium metal may not correspond to the real interface in the anode-less cell. So even though you obtain some interfacial resistance for the control system, it may reflect the real values. How do you think about that issue?
I mean, this is the interface here?
Yes.
Yeah, because I think all the components below this line would be metallic. So there will be two kind of transport phenomena here. One is going to be the electronic conduction, and the other is going to be the movement of lithium metal. So I don't think this interface is an issue because only the electronic conduction happens here, and maybe this interface is associated with the reduction of lithium ions. So there's going to be some resistance, as I showed you, but I don't think this interface is involved very much in the whole process of the polarization. That's
Okay,
my
thank you.
opinion.
Yeah, I have one more question. So these values were obtained at 60 degrees C?
No, it was obtained at room temperature, actually.
I see. So I just...
So it's bigger than the data we presented in our previous paper.
Okay, I was just curious about the activation energy for each resistance values.
Didn't measure it at different temperatures. We just measured it at room temperature. Maybe we can try later.
Okay, thank you. So any other question? You can type your question in the chat box or... Okay, so Dr. Lim, can you see in the chat box? I will read. Thanks much for the great talk from Professor Hui Wang. Quick question, how do these resistance change in batteries during cycling process?
What I can say, we haven't studied it systematically, but I can say that the resistance grows in general if we cycle a cell. And most of them, I think, from the cathode. And it also, I can say that it depends on the pressurization of the cell while we are cycling the cell. If we apply high pressure, usually the resistance increase is minimized. But if we don't have pressure on the cell, and then if we cycle the cell, then the resistance increase very high. Yeah, that's my answer.
Okay, so more question. You can just speak. I think it's a very good opportunity. So, okay. Then, can I ask more question?
Yes, please.
Okay, so in your Nature Energy paper, very small amount of solid electrolyte was used for the cathode. Maybe I remember 10%, something like that. So have you ever tried larger amount of solid electrolyte in the cathode layer? Then it may be possible to minimize the resistance of the cathode. Then
yeah, basically, if we increase the amount of electrolyte, we can reduce the polarization, and also we can improve the cyclability in general. But that's gonna also hurt the energy density, because if we have to decrease the amount of cathode active material in the cathode, so there's a kind of trade-off. And also, even though the amount of electrolyte is about 10 weight%, but the volumetric percent is going to be much higher because the lower density of the electrolyte compared to the density of cathode active materials. So we have to also consider that.
Thank you. Any more question?
Okay, I think I finished my talk quickly, so yeah.
Okay, so I think we don't have more questions. So let's thank Dr. Im again.